seminar in this online manner, so I'm sorry for this, but it is urgent issue. So 16 participants. Okay, I will not explain more. Please, Paweł Caputa, you are welcome.
Okay, so welcome everyone. I'm very happy to be here today. Unfortunately, I couldn't join the room, so really sorry for that. But normally I'm at room 566, so from Monday I'm very happy to discuss with you in person if anyone has more questions. So today I will tell you about geometry of Krylov complexity. And this is actually based on recent works with Javier Magan at the University of Pennsylvania and my student at Dimitrios Patramanis at UW, and also actually paper from today with Shuvik data from CERN that I will mention at the end if I have time. And the outline of my talk will be as follows. So I'll start from the subject of operator growth and Krylov complexity. Then I'll discuss the symmetry approach and then the geometric interpretation of Krylov complexity. And at the very end, I'll talk about the motivation, conclusions, and open question. So I decided to make a bit of an experiment because I usually start from, or people usually start from introduction and motivation, and that usually requires some history and politics. So I'll try to avoid this in my talk and I'll just go straight to business. And this way we can, I will hopefully not lose any of you on my motivation that may be from string theory or ADS CFT. And this will be only discussed at the end. So, sorry for a bit unusual format of the talk, but I hope this will be more useful for discussions from people from various backgrounds. Okay, so let me start with the definition of the operator growth. And I'll be generally talking about quantum mechanical systems. It can be actually quantum mechanics or quantum field theory and described by some Hamiltonian H. And we'll be interested in evolution of operators, this curly O, that is usually governed by the Heisenberg equation. So the time derivative of the operator, it's equal to the commutator with the Hamiltonian. And formally, we can write this time-dependent operator or the solution of this equation as basically the standard from quantum mechanics. So we have evolution, unitary evolution with e to the IHT of the operator at 0, and then its conjugate. And formally, we can write this time-dependent operator as some power series in the real, this will be, the t will be real Lorentzian time, and we can write it as a power series in t with operators that appear in this, given by where the first one will be just the standard operator O. That will be my operator O, curly O at 0. I will drop this this time from the operators for convenience, and then other operators in this power series will be nested commutators with the Hamiltonian. Okay, so for example, the first one will be the commutator of H with O, the second one the commutator of the commutator of H with O, and so on. Okay, and in this picture, or the physics of this operator growth, you can think about it as that basically a simple operator O at the initial time, as time progresses, spreads or evolves in the space, in a complex space of operators. So for example, yeah, you can think about some Pauli matrix or something supported on a single spin chain site, or some quantum field theory operator that is, let's say, simple in some sense at the very early times. And then once you do this evolution, the operator gets more and more complicated in this following sense, that it has to be written in terms of some very complicated operators as time progresses. And actually, a common law or some kind of intuition is that the more chaotic, in some sense, the Hamiltonian is, the faster the operator will grow. So if the Hamiltonian, for example, of a spin chain has several is supported on several sides, then this initial Pauli matrix will, with time, will become very complicated operator. And in some sense, the question I would like to understand better, or maybe a framework I would like to develop better, is basically how to quantify this this law. That how can we quantify? How can we make precise this intuition? That is for more complicated operators, and Hamiltonian, the operator will spread faster in some sense. So that will be the theme of my talk. Okay, and basically the main technology that I'll be using is somehow borrowed from condensed matter systems, or maybe even exactly solvable systems, and we'll be talking about it's actually usually goes under the name of the recursion method, and there's a nice book from the 60s by Viswanath and Miller that has basically all you need to know about this approach. But I'll review the basic things that will be needed in the rest of my talk. So formally, we can define the so-called Duvelian operator, which will be basically a Hamiltonian, this abstract space of operators, such that the action of the Duvelian on operators will be basically taking commutators of the original Hamiltonian with those operators. So in particular, this Heisenberg operator of t will be formally just exponent of I Duvelian times t acting on these initial operators. Or in other words, these operators that we write in the expansion of the Heisenberg operators, they can be seen as different powers of this Duvelian acting on the initial, say, perturbation. So the first one that we had before, this will be basically a formal way of writing these nested commutators. And basically, to quantify the growth of the operators in this method, we'll need a basis associated with all these different powers of the Duvelian acting on this initial operator O. And that's where the name comes from. This is the so-called Krylov Basis that was done a long time ago by basically generally this method, associating building a basis with different powers of a certain operator acting on a certain vector in the vector space. And what will also be important is the so-called inner product in the space of operators. So basically, once we will be building the state, we need to orthonormalize them. So this basis, we need to pick the inner product, and the standard way to do that will be to choose the so-called Whitman inner product, or basically for two operators, A and B, we'll be computing their inner product as the two-point correlator of B and A dagger in the thermal state. So this expectation value of beta is just a thermal expectation value of the operator. And then we'll be shifting the operator, this A dagger, in the thermal time by some beta over 2 unit. This will be not play so much role in the talk, even though it's actually very important and it's behind the whole thing. But basically, that will be the only part where I will use this inner product. But you should just keep it in mind that everything you can take it as a part of the definition. Everything that I'll be talking about will be based on the choice of this Whitman inner product for this Krylov space. And in some sense, there's some freedom in this choice. So we could have chosen any other inner product that is, in a mathematical sense. So we can define a family of inner products with some integral over thermal time and so on. I will not discuss that. I'll stick to this story in my talk. Okay, and once we have done this, basically, we want to use the so-called Lanczos algorithm for creating this basis. And for quantum mechanics, you can basically think about it as the Gram-Schmidt orthogonalization or orthonormalization of all these states. So in condensed matter, it's called the Lanczos algorithm. And basically, the algorithm goes as follows. We start with this initial state O0, and we take this as the state associated with the operator at t equal to 0. Then the state at O equal to, the state O1 will be basically the action of the Duvelian will be associated with the action of the Duvelian on the initial operator. And then the normalization of the state will be given by the CP1. This will be basically the norm of the state O1. And then generally we can repeat this algorithm. It's a recursive algorithm. That's why also the name recursion method, that will be defining some state an by action of the Duvelian on the state that orthonormal state that we already constructed. So this on minus 1, and we will be subtracting this on minus 2 with appropriate b in front of this state. And once we construct the states, then we'll simply normalize them by this bn, so such that the basis obtained is such that the orthonormal basis obtained this way with this inner product is done recursively for a given n, starting from this initial operator O. And this can be done, like what I'm talking about here is like extremely general. It can be done for any Hamiltonian and any operator in any theory. So, so there's nothing nothing fancy here yet. And basically this Lanczos algorithm it gives us, like, it can be run to arbitrary precision. Of course, you know, for a given theory to do it in practice, it might be very complicated and will require most often some numerical power. But in principle, the prescription is very clear and straightforward. So you can just give it to students and tell them to run to, I don't know, 1000 n and so on. And basically the result of this Lanczos algorithm for a given operator O and the Hamiltonian H is this orthonormal basis of these operators ONs. But also the Lanczos algorithm gives us these normalizations. And these normalizations are coefficients BNs. They are so-called, they have their own name, so-called Lanczos coefficients, and they will play a very important role in the rest of my talk. Okay, so are there any questions about this so far? Okay, so then let me proceed. And once we have, basically, once we have built this recursive basis, this Krylov basis, we can actually expand this operator, Heisenberg operator, in this basis. So we define basically the state O of t that corresponds to the state in the Krylov basis of the full operator at time t. And it is defined, you can think about it as basically exponent of the Duvelian in this Krylov basis acting on this initial state. And we can formally write it as sum over n, this I, this is imaginary I for convenience, you can put it out. And then you have this curly phi n's of t, on, and these are the coefficient expansions in this Krylov basis. And actually, these coefficients phi n, basically to fully fix the dynamics and to solve the problem of the operator evolution, we need to find these phi n's for a given operator. And actually, to find them, they satisfy a Schrödinger equation. So namely, when we take the t derivative of this state, we basically, on one hand, we just get the time derivative of the coefficients, but on the other hand, of course, we bring down this power of the Duvelian acting on the state. And actually, the action of the Duvelian on the Krylov basis, it's defined in the Lanczos algorithm. So if you appropriately normalize this an and move this state on the right, you can derive that Lanczos algorithm tells us that this Duvelian operator on the state on in the Krylov basis just takes you to the state on minus 1 with some Lanczos coefficients bn, and plus the state with Lanczos coefficients bn plus 1, state on plus 1. And if you compare now the coefficients of these two sums, you get the Schrödinger equation that this time derivative of the state phi, once you reshuffle the summations here and use this definition of the Duvelian on these guys, you get that this equation, this discrete Schrödinger equation, should be satisfied by this phi n's. So in other words, if you want to solve for the dynamics of the operator in your theory, using this Krylov basis, you just need to solve this. If I give you, you just go through this Lanczos algorithm to construct the basis, and that will give you these bn's. You just plug them to the Schrödinger equation and you solve it with the initial condition that this coefficient at time equal to 0 should be just delta n equal to 0. And this is precisely the solution of the whole problem, without even going to the specific details of your Hamiltonian and operator O. This algorithm can be done to the very end, and basically this phi n's, this is something you are after.
Can I have a question?
Yes, please.
Okay, so I understand that you wrote this Duvelian, as a Jacobi method.
Yes.
So this is a Jacobi method. So it's not. Is it obvious that this operator in this basis is self-adjoint? Because to make to compute the evolution. So if you have an equation like the one at the end. So if these coefficients b are chosen in the not a proper way, then it may happen that you don't have the unique evolution.
Yes.
So is it obvious that in your case you have always a unique solution?
Yeah, this I'm not 100% sure if I can make this in general, like answer this question in general. I would assume that maybe somehow this Lanczos algorithm is built in such a way that probably yes, but I mean, definitely in all the examples I studied and people studied, I think this is true, but I don't know like how to prove it in an obvious way. Like,
okay.
Yeah. Thanks. Yeah, but I think this is what I presented here is as maybe in some sense too general. So I'm afraid to make a strong statement. Probably there are some examples of choosing some Duvelian or Hamilton where what you're saying might be important. Okay. Yeah. Okay, great. And let me just say that in some sense, this is also an important part of this recursion method, is that basically usually in condensed matter or many body systems, this recursion method starts from the so-called autocorrelators. So autocorrelator will be basically, once you have chosen this inner product, it will be an overlap between your initial state O and the state at time t. So you can think about this as a probability amplitude of doing an evolution and staying in the same state. Or this is in this Krylov basis is defined basically an expectation value of e to the Duvelian, or in the expansion is this coefficient 0 or in the Krylov basis. And actually this autocorrelator, the moments of this autocorrelator, so defined as derivatives with respect to time, they are related to these Lanczos coefficients bn's by some appropriate determinant of some matrix. So you can actually construct an algorithm starting from this autocorrelator. You can also construct an algorithm and find these bn's, and then basically plug them to the Schrödinger equation and find the solution in some other way. So there are many ways of getting these bn's, not directly related to this Lanczos algorithm, but in some sense they are all equivalent. And sometimes this is kind of a useful or maybe efficient way of doing these things, in a sense that basically this autocorrelators, they're usually difficult to obtain. So it takes a bit of maybe numerical power for a given Hamiltonian and given operator to find what is this autocorrelator, but they are known explicitly in many models. For example, for 2D CFTs on the line, for a certain inner product, or integrable models, or random matrices, or SYK model. And actually, this is another useful way of checking consistency, that if you solve your recursion relation for a certain operator in a certain theory, if you know the autocorrelator, you can check that this answer should be the same as the one from the autocorrelator. And for example, in SYK model, we know this autocorrelator. If you don't know what SYK model is, that doesn't matter. Like, you can just think about some model that I maybe mention at the end what it has to do, let's say, with my political motivation of holography. But you can think about this certain model that is interesting for us as basically a model with autocorrelator of this type, that this probability of doing evolution in this model and staying at the same initial state is basically goes like inverse cosine. So it's actually exponentially suppressed for late times. So that means that model really does something to your operator such that it's really not staying in the initial state. Okay, that's just a comment for people that maybe know something about this SYK story. Okay, and then basically the main object to quantify this growth of the operator is the so-called Krylov complexity, or K complexity. And basically, the way to define it is it is useful to think about this problem in the following way. So this physics of the growth or physics of this discrete Schrödinger equation can be basically thought as the motion, interpreted as a motion of a particle on a certain chain. So let's say we draw this certain, you can think about it as some spin chain where the nodes of these chains are labeled by these amplitudes that we expanded the operator in the Krylov basis. So these amplitudes phi n's here. And as time progresses, the particle starts at this initial phi 0 and then moves to the right. It jumps to the certain more complicated phi n's with probabilities b1, b2. These are these Lanczos coefficients bn's. So, and when I'm talking about probabilities, I mean, that means like the sum over all these amplitudes, this phi n square is equal to 1. And basically, the farther the particle is on the chain, the more complex the state in the Krylov basis needs to be employed to represent the operator. So initially, the state phi 0 was very simple for a simple operator, but as particle moves, as time progresses, you really need to represent this operator in, for example, phi 3 and phi n, blah, 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 and so on. And you remember, these are the states that are that correspond to these nested commutators of the Hamiltonian with initial operators. So they are very complicated in this sense. And then this motivated people in this many-body systems or condensed matter to define this notion of K complexity or Krylov complexity as basically an average position of this particle on the chain. So this is some kind of physical motivation of how you could represent this complexity of a certain operator. So in other words, I'll be talking about this KO as a sum over these probabilities with an expectation value. It's as an expectation value of n or average position on this chain for any given model defined by this amplitude phi n of t. And this complexity depends, let me just mention one more time. So this complexity depends on the given operator for which we build the Krylov basis, as well as on the Hamiltonian that kind of enters into this Krylov basis via the Duvelian. And sometimes it is useful also to think about this complexity as an operator. So basically you can write this operator in this Krylov basis as sum over n. And then this complexity KO, you can think about it as an expectation value of this Krylov complexity operator in this state O of t. This is also a bit, there might be some subtleties in this definition, but in most of the cases I'll be considering this is truly the case. Okay. And now let's go to physics. So basically there was an interesting recent paper, recent from 2019 by a group at Berkeley that studied precisely this question of the operator growth in various models, from lower dimensional cases where you can really do the numerics on some spin chain, to really models like SYK, where you know this autocorrelator that I showed you before, to maybe complicated higher dimensional systems. And from their studies, they noticed actually that the growth, you could characterize the growth of the operators, or basically different models, by the properties of the growth of these Lanczos coefficients. So basically they noticed that if model, here on this plot from their paper, you can see these Lanczos coefficients as functions of n. And here you can see, for example, if the model is free, these Lanczos coefficients, they don't really grow with n, they are usually constant. When the model is kind of in the class of integrable models, these Lanczos coefficients for large n, they grow, but rather slowly. But when the model is really chaotic in some precise sense, then actually these Lanczos coefficients grow linearly with n with some characteristic coefficient alpha. And also there is a constant piece gamma and some order 1 terms. There are some modifications to these laws in very low dimensions, but this will not be so important for us. And they notice actually that there's a saturation of this bound for the growth over Lanczos coefficients that happens for maximally chaotic systems. And this maximal chaos, what they define is, it's something that is reminiscent from the so-called out-of-time ordered correlators. These are some recent probes of quantum chaos that have been used in holographic, but also like by now they are lifted to all many-body systems. And these are basically some 4-point correlators of certain operators, and these correlators, from these correlators we can extract certain Lyapunov exponent, and by this Lyapunov exponent we can tell if the theory is theory is integrable or chaotic, and in particular in these maximally chaotic theories, this Lyapunov exponent is given by 2 pi over, is basically proportional to the temperature of a particular model. So when I mean when they mean maximally chaotic here is really in the systems in the notion of maximal chaos characterized by this out of time order correlators. Okay, so they also pointed that when this maximal growth of Lanczos coefficients is saturated, this is shown in this Krylov complexity as an exponential growth. So when bn's are basically alpha times n, once you solve the Schrödinger equation and compute the Krylov complexity for a given operator, then the growth will be exponential, and the so-called Lyapunov exponent of this growth that appears here is directly related to this coefficients of the growth of Lanczos coefficients, namely this lambda equals to 2 pi alpha. And basically, you can do this explicitly for the so-called SYK model. So you can basically think about this model, as I told you here, as the model given by this autocorrelator inverse cosine hyperbolic. And then for that, once you go through this Lanczos procedure, you find that these Lanczos coefficients have this form, pi over beta, square root of n, eta plus n minus 1. So actually, you can check that for large n, these Lanczos coefficients precisely grow as n, grow linearly with n. And the Lyapunov exponent extracted from these Lanczos coefficients is given by 2 pi over beta. And in fact, this is this maximal Lyapunov exponent that was also found in the out of time order correlators for the SYK model. And interestingly, you can also solve this Schrödinger equation that we talked about here for this SYK Lanczos coefficients with this initial condition. And actually, you're going to find this answer. So this answer depends on this eta. This is this power of the growth of the autocorrelator, and also it depends on time, of course, and also depends on this coefficient alpha in the growth of Lanczos coefficients. And so once you have this, you can compute this Krylov complexity, and this complexity becomes simply the sine hyperbolic square alpha t. So basically for large time, this gives you this Lyapunov coefficient here, given by 2 pi over beta. This example actually will be important in the rest of my talk, and actually the form of it. So I want you to stare for it for a second, and then maybe before I go to the next part, let me ask if there are any questions at this moment, or about the universal operator growth hypothesis of this people.
If you compute here this index of complexity, it depends on parameters, yes?
Yes.
And what can you say when you look into this? So the value of this indicates less. If it is low, you have less problems to compute things, or what is the meaning of this complexity index?
What is the meaning of this complexity index? Well, you at least from these rough estimates of these guys, you will know that at least in these models, if you compute other observables, for example, this out of time order correlators or maybe entanglement entropy, they will grow much faster than the ones in integrable models. So in some sense, it's kind of a probe or some, well, not order parameter, but some kind of first approximation to basically say if the model is chaotic or not. That's the claim. But generally, you know, depending on the part, this thing is quite universal. Maybe you will see once you give me a Hamiltonian of a particular type, let's say even for harmonic oscillator with certain frequency and so on, this alpha or this Lyapunov exponent will depend on the details of this Hamiltonian, as well as on, for example, this temperature, like some notion of this inner product that I introduced at the very beginning. But in some sense, it's just a probe to tell you that, you know, the model is in a certain class, just this quantity. But then you can use more fine probes of this model to tell you, like, okay, what are the consequences of this model being chaotic or integrable or not? But for my talk and for this story, what will be important is basically just to characterize or to say, characterize the classes of this operator growth, let's say. So if we have this behavior of this Krylov complexity, that means that operators in this model grow in a very, very fast manner, in a very chaotic manner.
Okay, thank you.
Oh, excuse me, can you hear me?
Yeah.
So I have very nice question about the bound of the BM. It's the first line. So.
Yeah. Oh, sorry, I cannot hear you.
Hello?
Yes, I can hear you now.
Yeah, so gamma is constant, right, in this line?
Yes.
But it plus some order 1, right? So it's also kind of constant, right? So what is the difference? Like how to distinguish gamma and the other order 1?
Sorry. Yeah, sorry. Yeah, I meant, I think this order 1, the gamma should be in the order 1 parts, sorry. There was also some logarithmic corrections, and maybe that's why I was writing it like this, sorry.
Okay, so do you have the kind of the physical interpretation for this gamma?
Usually they are not universal. So many details of the Hamiltonian will enter these gammas, and as far as I know from these numerical studies, there hasn't been so much universal interpretation as for the alpha. But I think it's an interesting question to what can we we'll learn from this gamma in general. I don't know.
Okay, yeah, thank you.
Thanks. Okay, so I left this for a bit and hope you kind of maybe to some of you it already looks familiar, but if not, this will be the second part of my talk. So basically, when we jump into this story with my student and Javier, we before, in some sense, we have been working a bit on complexity and definitions of complexity in many body systems and quantum field theories. So that was our background. And we wanted to understand what is actually the operational meaning of this Krylov complexity in a sense of usual approaches to, say, circuit complexity and so on. If you're not familiar also with the circuit complexity, that doesn't matter. It will not play an important role. And then we wanted to understand what is actually the meaning of these BNs. Like, how can we really, why are they so useful that we can characterize the system by these BNs? And then in particular, we wanted to understand what determines exactly this exponential growth of Krylov complexity. How can we say that a certain model is chaotic versus integrable based on some universal general principles? Like, do we really need to study the, are we only tied with the numerics? Do we really need to do the same thing, the evolution of the operator for every possible model to learn something? That was really our question. In some sense, this was really motivated by this classification and generalization and basically analytical understanding, but we are very poor with numerics. So we really wanted to, we were really interested in the question of operator growth, but we were kind of discouraged by the numerical approaches that were studied in most of the condensed matter systems. So that's what we wanted to do. And of course, if you are usually not very strong with numerics, you want to ask questions like, okay, can we use the symmetry to maybe determine the problem or solve the problem from maybe a different angle? And in particular, a strong, we were kind of this approach to SYK that was maybe not exactly condensed matter, but that was used in this Berkeley paper that I mentioned. It actually comes from holography, and it has been quite extensively studied in the context of ADS CFT. So we actually knew that there is an SL2R symmetry that determines the evolution and basically many things in this model strongly. But somehow, in the way the operator evolution was solved in the SYK was not obviously showing the symmetry. So we wanted to understand, maybe we could explore this SL2R in a better way. And finally, well, we wanted to understand if this Lanczos complexity somehow could be thought of as some kind of circuit complexity. Well, I just told you that you will not need it, but let me just say that basically all you need to know about circuit complexity is that we tend to think about certain states, for example, as being created by a certain circuit of starting from some initial state to some target state of t. And this unitary circuit, in this case of the operator growth, could be given by exponent of this Liouvillean. So the question we wanted to ask is, can we think about these circuits of the Liouvillean in some kind of geometric way? Okay, and with these questions, let me go to maybe description of our work. So basically, let me go back to this definition of the Liouvillean. I told you that this Liouvillean operator in this Krylov basis is actually is tridiagonal in general. So in other words, when it acts on the vector On, it gives us this Bn's On minus 1 plus Bn plus 1 On plus 1. So if you compute its matrix representation in the Krylov basis, in general, it can have some elements on the diagonal. For the operator growth, they are all 0. They don't play any role. And then basically this Bn, these Lanczos coefficients, they appear as this off-diagonal matrix of the Liouvillean in this basis. So actually, maybe a natural question to ask is that maybe, or maybe a simple approach to this problem is that maybe we could define this Liouvillean operator or representation of this operator in this Krylov basis in terms of certain ladder operators. So basically, if you think about the Liouvillean as basically some alpha times some raising operator plus a lowering operator, such that when this ladder operator act on some vector On and gives me this Bn is an eigen, well, it gives me Bn plus 1 times On plus 1, or alpha minus On gives me Bn times On minus 1. This would be very powerful representation, and that could shed light on this basically ingredients of these Lanczos coefficients, if this was the case. And so in other words, if this Liouvillean was that's where the symmetry comes into, if the Liouvillean was a part, or these ladder operators were part of some Lie algebra, then actually this would give us a lot of predictive power and give us a nice interpretation for the Bn's without doing any numerics. And of course, maybe for people from a bit older generation or that studied this kind of many-body, exactly solvable many-body systems, this is something very natural. These notions of symmetry generating algebras or spectrum generating, I think that was the name, generating algebras was very common in the past when people studied certain evolution of with Hamiltonians, that you could write these Hamiltonians in terms of certain algebra generators, and that was usually a very beautiful story that that allowed for exactly solvable exact solutions of certain systems. So basically, we wanted to use these intuitions, but somehow now into the Liouvillean and this Krylov basis and see if this takes us anywhere. Is this motivation clear? Okay, so let me just, sorry, are you with me? Can you hear me?
Yes, yes.
Okay, I was wondering. So let me actually now do this for the SL2R. Basically, if we apply this idea to SL2R, as you know, SL2R is given by is Lie algebra given by three generators, L0, L1, and L-1. They satisfy these commutation relations. And in this case, the Liouvillean represented in the Krylov basis could be written as this alpha times L-1 plus L1. And actually, we can just write down the representations for the SL2R, namely, if we write down the states labeled by some index H, this is basically some highest weight state. And then we act on this highest weight state with n power of the creation operators, L-1, and we normalize them appropriately. Then these generators L0, L1, and L-1, they have a very simple action in this Lie algebra basis. In other words, in particular, what is important is that this L-1 acting on this state just gives you this thing, and L1 acting on the state Hn gives you this n to h plus n minus 1 acting on times h n minus 1. So in particular, if you stare at this expression, and if you remember my results or these results for the SYK, it is very, if you you can basically guess what should be the answer. You can just associate the Krylov Basis state ON with this Lie algebra HN. And then if you remember from the definition of the Duvelian, you basically need to, if you write the Duvelian in terms of ladder operators, basically these Lanczos coefficients that were obtained by this complicated recursive algorithm should be the coefficients that appear in front of the state n-1 after you acted with the Duvelian, and that's precisely here. So if you look at the lowering operator on the HN, you can see alpha times this one. It gives us precisely the BNs of the SYK model. So actually, what we can make precise is exactly this, using the symmetry ideas to the SYK, and we can make transparent the appearance of the SL2R symmetry to fix the whole structure of the model. Maybe if you see it for the first time, this is not so, maybe it's not so surprising if you know this explicit form of the solution, but actually if you have tried to solve this model or try to go for this recursive procedure, especially numerically or for some particular example, you should be pretty amazed how easy these things pop up if you just use this symmetry approach to the model.
Can I have a question?
Yes, please.
So which kind of representation it is?
So here in this part of the case, in this part of the talk, and in most of my cases, I'll be using discrete series representations of a set.
Thank you.
Thanks. Okay, and actually, this brings us also to another beautiful topic that maybe many of you are very familiar, namely the coherent states or generalized coherent states for various Lie groups. And actually, if you look at this operator of T that is obtained by e to the I LT on the O, when you're in the symmetry scenario that the Duvelian is given by alpha L minus 1 plus L1, you should actually, this should remind you that actually this operator, the unitary evolution with the Duvelian, is nothing but a certain special case of a displacement operator for SU1, or SL2R in this particular case. So actually, the state that we are talking about, if we associate, sorry, let me basically also, maybe this is important here, this state associated with operator O of 0 is just the highest weight state H here. So that's important. And if you think about this state expanded in this Krylov basis for the symmetry scenario, actually this becomes nothing but a certain displacement operator of this generalized symmetry acting on this highest weight state. And these displacement operators, maybe if you remember from some quantum mechanics, they can be parameterized by complex parameter xi. It's useful to write it in coordinates rho and phi. This rho goes from 0 to infinity, and phi is between 0 and 2 pi. And then we can also write a complex coordinate z that is related by this that is given by tangent hyperbolic rho over 2 e to the phi. And for SU1, or SL2R, this coherent state, they parameterize the unit disk. So we are interested in the set, in the family of coherent states labeled by the z and h, such that the z is within the unit disk. So now if you stare explicitly at this coherent state from for SU1, or SL2R, these are the so-called parallel of coherent states. This is given by this form. If you compare this with the SYK answer, so I'm bringing you here, this is the explicit solution of the Schrödinger equation for the SYK model. You can recognize this tangent hyperbolic and this gammas here. What you see is that actually this growth of the operator, as you obtain by the solution of this Lanczos approach, is nothing but the coherent state for the particular value of this rho. So rho equals to 2 times alpha t, and phi equals to pi over 2. So in other words, you can think about this state that is very interesting for us, this Krylov basis state, as a coherent state for this particular value of the complex parameter. And maybe a better way to say this is that this operator growth is actually a trajectory in a phase space given by this coordinates rho alpha over t and phi equals to pi over 2. That's just that's the interpretation that will be important in the rest of my talk. And again, let me remind you that this was all possible by representing the Duvelian by this ladder operators in this Krylov space. Okay, and then there's another important thing that we'll use from the story of coherent states, namely the so-called Fubini study metric. Maybe in various communities, this goes under the name of information metric. So once we have basically this coherent state for these explicit examples, we can associate the metric with them, a natural metric in phase space given simply obtained by taking the variation of this dz and subtracting the overlap between the state and its variation. And basically for the SL2R, this geometry becomes nothing but the hyperbolic disk. So it can be written in terms of complex coordinate or this rho and phi. And this geometry is negatively curved. The curvature is given by -4/h. And as I was saying, the operator growth, as we study for the SYK model, for example, is nothing but geodesic in this manifold or geodesic in this phase space given by rho equals to alpha t and at fixed phi equals to pi/2. Moreover, we can observe a universal relation between this Krylov complexity that I defined before and the volume in this geometry. So in other words, if we compute the volume in this metric up to this rho equals to 2 alpha t, this is given by this sine hyperbolic square of alpha t proportional to that. You can check that maybe you remember from the computation of SYK, this volume is nothing but pi times the Krylov complexity of operator O. And this geometric interpretation holds in all the examples that we studied. So in our paper, we considered various other, you say, generalized coherent states in the algebras and then computed basically operator growth scenarios. And it's always for various trajectories for various geometries, we can see this we can interpret this Krylov complexity of a certain operator as a volume in this Fubini study metric. So in other words, this is a cartoon. Geometrically, we can think about this operator growth as a certain trajectory, this operator that in this Fubini study metric or this hyperbolic disk, such that at t equal to 0, we start with some operator at the rho equals to 0. And then as time progresses, this operator goes along the direction phi equals to pi/2. And if we stop the operator at some point, at some time t, or at some, that tells us which rho we are at, and we compute the volume or the area encircled by this unit disk, that's proportional, that's just pi times this Krylov complexity. Okay. Are there any questions about this? Okay. So how much time do I have? If I show more examples or?
Can I have a question? Sorry.
Yes, please.
Unfortunately, I did not hear probably every word, but this space you are discussing now, is it just the space of this quantum states? Does it have anything to do with some dual geometry or?
At this moment, no. This is just this is a space of coherent states of SU1,1.
And will you discuss it? I'm not sure how much time you have. Anything related to some dual?
Maybe this is something still in progress, and I'll maybe mention some things at the end. But for this talk, it's.
Well, this is gravity seminar. This is why I'm asking.
yes. Sorry. I'll maybe mention something at the end in the politics section.
Okay.
Okay. So yeah, let me maybe show one more example to really convince you that the symmetry approach is pretty powerful to quantify various growths of the operator and various classes of the evolution. So we can do the same for SU2, for example, and we take the Duvelian to be alpha times. By the way, what is important is that in the symmetry approach, this was all maybe Jacek asked this question at the very beginning. When we think about the symmetry approach, also for this 2R, this alpha that I'm talking about here is the same alpha that appears in this Lyapunov exponent and in the growth of betas. So in some sense, you can see when you, and of course, Duvelian is related to the Hamiltonian, but in some sense, when we think about the symmetry, this we cannot fix this alpha, like alpha is just some coefficient. And then basically to write the Duvelian in this way, we need to know what the Hamiltonian that had this symmetry structure is. And then the details of this Hamiltonian will enter into this alpha. But when we talk about symmetry, we don't really need to know these details. We just need to know that, okay, the operator growth in a certain theory can be represented by this particular Duvelian of this symmetry, okay? Okay, great. So maybe to contrast this, in some sense, this exponential growth of complexity and this chaotic SL2R example, we can look actually also at SU2. So basically everything from this story goes through for the SU2. You can define Duvelian in terms of rising and lowering operators. And then you can build a representation. Again, we'll be interested in this discrete series representation by starting for convenience at some state spin J representation. We start from some J minus one. Sorry, we start from some state labeled by J minus J, and then we act with the creation operators on this. And then, as you remember, for SU2, we only have like 2J plus 1 state for a given representation J. So in this case, we can again we can associate these algebra states with a certain operator growth in particular models that allows us to read off BNs, these Lanczos coefficients, if we wanted to extract them by this Lanczos procedure. And you can see here that these BNs for SU2, they don't grow, N cannot go bigger than 2J. So actually they max for some period of time. They are actually drawn here. They grow like square root of N, but then they are maximized for some particular value, J plus 1/2, and then they come back to some particular almost initial value for the value 2J. So maybe from this, the lesson from this one is that for maybe integrable models, you don't have an infinite number of states or infinite Hilbert space or phase space to explore by this operator, but rather a finite one. And the growth of this Lanczos coefficients is submaximal. Also from here, you can actually expand, as also in the SL2R, there was a question maybe by Shaw that you can compute what is this subleading coefficients in the large N expansion, and this subleading coefficient in the previous case is related to the dimension of the representation in the symmetry scenario, at least. Okay, so we can compute actually this, and then of course these coherent states for SU2, they are very well known. So for this Duvelian, we can again write down coherent states, and we can read off, we can find the solution. So once we have these BNs, we can plug them to Schrödinger equation, we can solve it. And we can find what are these amplitudes, let's say, in the expansion of the operator in this basis, and we can see that this is nothing but the trajectory in this phase space of spin coherent states given by this theta parameter to alpha t, and then at particular angle phi equals to pi over 2. And once we compute the Krylov complexity, this Krylov complexity is actually oscillating. So for spin j, it becomes sine square over alpha t. So at initial time, it grows like t squared, but then very quickly saturates and actually is recursive. So this is a very strong hint that the model that would be described by this Duvelian is given by some, well, it's not chaotic. And again, there's a story between Fubini study geometry that is now a sphere and the volume up to time t in this geometry is simply pi times this Krylov complex. Okay. Maybe I'm almost out of time.
No, wait. How much time? 10 minutes you have.
Okay. Oh, great. Okay, because I just remember that I started slightly late. So let me maybe just say one thing. So actually the symmetry approach, and we studied also here various examples, like maybe for Heisenberg-Weil algebra, and also basically you can take your favorite coherent state and play with this story and now try to check what kind of geometry they correspond to and what kind of growth of operator they would imply in this classification picture. But actually, we can go beyond that. The symmetry actually teaches us an interesting lesson that we can apply to more general models. And the lesson is as follows. So basically, I told you that we started with the Duvelian that has this tri-diagonal form in the Krylov basis that is given by ON this particular way. You can actually define another operator B, basically that is simply related to this another change of the basis in this space of abstract ladder operators. So Duvelian, I told you we talked about Duvelian as sum of rising and lowering operators. You can define this operator B as some rising minus lowering operator. And basically, what you need to know, you can define it simply by an algorithm, the same way as you define a Duvelian for any model. It doesn't have to be in any symmetry sector. It's basically this action BOON is minus BN, ON minus 1 plus BN plus minus 1. And once you define those two operators, we tell you, okay, just start commuting them. So basically, once you start commuting them, at the first step, you arrive at some operator K tilde that can be written as the commutator of L and B. And its action on the Krylov basis can be simply fixed by these definitions. It's given by this polynomial of Lanczos coefficients. And let's say now, this was in fact the case, that's how we came to this story. This was in fact the case in all our examples. Let's say that demand that this algebra of these operators in the Krylov basis closes at the first step. So let's say that, you know, this commutator already forms the closed algebra with L and B. If this is the case, you basically all these operators have to commute with each other with some coefficients. You can check that if this is the case, then this polynomial that appears here can be at most linear in N. So for some constant A and B, this combination has to be given by AN plus B if you want that at this step the algebra is closed. And if this is the case, you can then solve this polynomial equation with a given initial condition that this B ends at n equal to 0, there 0. And this gives you this Lanczos coefficients for this particular, basically from the closure of the algebra. And in fact, this all our like SL2R, SU2, Heisenberg, Weil, and various algebras, they form into this story. But actually, the interesting question that we can propose, the interesting lesson that we propose from this story is basically what if it doesn't. So basically, let's say that you have your physical Hamiltonian of some many-body system that maybe, you know, it's some deformation of a certain symmetry algebra. Then you can basically, this is a general definition that holds for any theory. You can perform this commutator, and then you can check, you get something, and that gives you some constraints for Bn. But then this does not close the algebra. You get some other operator, then commute it with the rest, and then check what happens. And then at some point, maybe your algebra closes. This gives you a system of polynomial equations for these Lanczos coefficients. So this general idea can help us in maybe more symmetry like classification of this operator growth instead of just, you know, doing this numerically for any possible Hamiltonian that you can find there in the literature if your computer is infinitely powerful. So that's what we propose based on these examples. And then for the SL2R, this is actually very nice because basically this Duvelian that we're in the Krylov basis that is given by this object, also B that is given by this L1 plus L minus 1, and this operator K tilde that comes from the commutator, they are just related to L0, L1, L minus 1. And basically they are nothing but directly related to the symmetry of this ADS2. So they are basically, you can write them as killing, in terms of killing vectors of this two-dimensional geometry. And in particular, this operator K tilde that is very closely related to the Duvelian, basically, to this Krylov complexity operator that I talked about at the very beginning. It's simply the generator of translation in this phi direction in this geometry. And actually, maybe this is a small answer to Piotr's question. There has been a lot of works in this lower dimensional holography, especially this work by Maldacena, Lin, and Zhao, claiming that there should be some notion of complexity like maybe associated with the operators, that grows exponentially and is closely related to the symmetry of the near horizon geometry of certain black holes in ADS-CFT. And universally, this the near horizon geometry of black holes is ADS2, even though one has to be a bit careful about the Euclidean versus Lorentzian, but we claim that this is one of the instances of this identification between the complexity or growth of operators and the near horizon symmetry of certain holographic black holes. Okay, so with that, I think I can finally go to my introduction and motivation, unless there are any questions up to now. Okay, so let me just tell you now, I hope I gave you a kind of, say, motivation-free talk on certain technical things that I find very interesting that have to do with operator growth, and you can study them in various setups, from your favorite quantum mechanical models to quantum field theories and so on. And basically, the important thing there was this notion of symmetry and generalized coherent states that played a nice role. And I think that's valid, and that's generally applicable to many other systems. But my original motivation, the reason I'm doing, is as follows. So basically, in ADS-CFT, or ADS-CFT is some certain dictionary between certain holographic conformal field theories and geometry. Usually, it's some geometry of anti-de Sitter spacetime. And we have several explicit examples of ADS-CFT, but in general, we would like to understand some basic facts about ADS-CFT, namely what makes certain CFTs holographic. Let's say, you take your favorite 2D Ising model and so on and so forth, and you can ask, is this model holographic or not? If it is, what makes it holographic? What properties of the CFT assure me that this model is holographic? In particular, what we are interested in is how CFT states encode this holographic geometry of dual ADS. And one important hint is that entanglement in this structure of entanglement in states of CFTs is very important on hint on the properties of dual geometry. And maybe for people familiar with that, this dual geometry is explored by so-called Ryuta-Kayanagi surfaces that are dual to this entanglement CFT states. So in some sense, we have this new direction in ADS-CFT where we study and apply quantum information tools to explore the CFTs from the perspective of holography. But sometimes we actually have examples that entanglement entropy, at least in CFTs, is not always enough to fully determine the gravitational dual geometry. So, for example, we have some geometries where these Ryuta-Kayanagi surfaces, they saturate very quickly when we do some time evolution. But we know that the states in CFT, they still evolve with the states or operators in CFTs, they still evolve with time. So in some sense, we need more fine-grained probes of conformal field theories or ADS-CFTs, and we are looking for some probes of complexity. This is like in quotation marks because we still don't have like a very good notion of complexity that we could apply to this problem. And in other words, we would like to understand if there's a good universal notion of CFT complexity that is widely applicable not only to, say, to free theories and so on, but really to CFTs that are holographic, and this notion of complexity is maybe sensitive, is more sensitive than entanglement entropy, and we can fully determine this holographic geometry. So in some sense, that's my intro and motivation, and I hope like some of you would be turned off by some of these questions, so that's why I put it at the very end, and you can appreciate it that you could digest all the information in the talk without this politics. Okay. But in most of my talk, I discussed, so maybe actually now, am I already done with time?
Yeah. If you want to say something, do it.
Okay, so maybe I just say one more thing. Basically, everything I talked about, it was very, either very universal or kind of quantum mechanical based on symmetries. And but here I'm talking about CFTs. So actually, let me just basically tell you one word about this paper that appeared today. So CFTs that we want to study are basically some quantum mechanical models where we can again basically study the growth of the operators or the evolution of the operators. But in those cases, the symmetry that underlines the model usually, at least for 2D CFTs, is this Virasoro algebra. So basically we have some stress tensor, and then the modes of the stress tensor form the Virasoro algebra for a certain central charge C. And then basically these coherent states that I talked about here, they also play a very important role. We can use the so-called Fogg-Bargmann representations for these coherent states and represent operator growth in terms of these complicated coherent states in this Virasoro algebra. But what is nice, maybe, this looks like complicated formulas, but what is important is that we can again take this Duvelian of L1 and L-1 of SL2R, that is actually a global part of the Virasoro, and we can expand this operator growth now not in this powers of L-1 as for SL2R, but we can expand this operator growth in the full Virasoro geometry. And this formula looks complicated, but it's usually better to think about it pictorially. So actually, you can think of, for 2D CFTs, you can basically, when you apply this L1 and L-1 operators, what they take you is that they start from some highest weight state, or say primary operator, and they take you into some higher descendants level. So basically, descendants in CFTs are some operator that are obtained by taking some OP with the stress tensor and doing some integral, or basically taking these Virasoro modes and acting on the highest weight states. And for example, then the Duvelian that I talked about, this L1 and L-1, and its action, and actually the operator growth can be nicely pictured into the CFT as a growth on the Young lattice. So you should think about the operator growth as starting from this initial state here and going, as time progressing, going in that direction. And basically the operator becomes more and more complicated, and it's somehow now the probability that I talked about before for SL2R, it's now the probability on the space on the Young lattice in a particular way. So a nice pictorial example is here that, for example, for some up to descendant level 10, some initial simple operator, as time progresses, it becomes like, it kind of spreads into the bath of descendants in the Virasoro module. So this is just to convince you that these ideas of the operator growth, they can be generalized to more complicated systems in quantum mechanics, and in particular CFTs and so on. Okay, so let me just finish here. I wanted to tell you today that this Krylov complexity is a new and good candidate for the operator complexity in quantum field theories, in particular in CFTs. It allows us to distinguish between certain chaotic and non-chaotic theories. And that's actually, I did not talk much about it, but that's very important aspect of a CFT, this chaos in certain states to be holographic. And then in my approach that I talked about, we propose to look at this Duvelian and maybe these many-body algorithms from a new angle of symmetry, and then explore the power of coherent states. And this also allows us for a geometric interpretation of this Krylov complexity with many desired features from complexity in holography. I didn't talk much about this, but maybe for people that are experts on holography, this is important. And there's still many open questions, like, for example, we can study more generalized coherent states and for other Lie groups and try to associate them with operator growth in integrable or chaotic systems. For example, what is the size, the step after which the algebra of Duvelian and the other operators terminates? Does that play an interesting role in this distinguishing between chaotic and integrable? That's still an open question. And finally, actually, maybe there is more mathematical questions. There are more mathematical questions about this growth of Lanczos coefficients. Can we make some mathematical proof? Like, it seems like problem is well defined. We have, well, from the mathematical perspective, we have certain functions, let's say these autocorrelators and so on. And then we can expand these autocorrelators in terms of moments, and moments are related to these BNs. So actually in mathematics, there's lots of this kind of growth or maximal growth hypothesis literature, and they are usually related to something called Bieber-Bach conjecture. Maybe there would be a nice way to understand mathematically what makes is this bound true, and what makes it important for physics. Like, can we really prove that under certain conditions, maybe locality of the Hamiltonian, I don't know, or what else, then these BNs cannot really grow faster than n? That's still an open question. And finally, there's this connection to holography and near horizon geometries. That's something that we are working on now and exploring in more details. I didn't have much to talk about it, but if you want to discuss, I'm more than happy to do that in 566 from Monday. Thank you.
Thank you very much. And time for questions. Oh.
I may have another question. I'm not sure if I understood or heard everything properly, but is there some definition of this complexity beyond CFTs?
Oh, certainly. For this Krylov complexity, it can be done for arbitrary quantum mechanical systems, as I was explaining from the beginning of my talk.
Okay.
Sorry. So this is basically for any quantum mechanical Hamiltonian H and operator O. We can go for this Lanczos algorithm and then expand this operator. And then once we have this expansion, we define a complexity of this operator growth on in the Krylov basis. So there's, yeah, in fact, this definition and this notion comes from condensed matter and many body systems. It's something that only in CFT, the story of this in CFT has maybe a few months or maybe definitely less than half a year.
Other questions?
Hello, can you hear me?
Yes.
Okay. So yeah, thank you for your nice talk. So I have a very nice question about the bound of Bn again. So can you show me that other slide? Okay, so I have a very nice question. So why is linear alpha m? Or yeah.
This is a phenomenological observation.
It's just an observation?
Yes. So this people, Parker et al., the group at Berkeley, they studied this operator growth and Lanczos coefficients in basically a zoo of model that they could either solve explicitly by doing this Lanczos algorithm or find in the literature. And they noticed that one can make this universal operator growth hypothesis and conjecture that no matter which model you study, they never grow more than n.
Okay, but in this case, it's basically kind of a CFT, right?
No. So for the SYK model, the SYK model saturates this. But they studied like XX, Ising, SYK, various examples. Like actually, SYK does not, even SYK is not a CFT. Like it has a conformal limit at some point for this operator, but they studied it for general SYK, and this was this bound was still there. And but actually, like in many models that actually had these BNs in the literature, they also went back to these examples, and they saw that this growth of Lanczos is always like that. It's never more than linear.
Okay, thank you so much.
Other questions?
The near horizon geometries. Why you expect any relation?
sorry, I'm not sure if I heard correctly. The question is, why do we expect the connection between complexity?
Don't analyze the words which I use. The question is, what is expected relation between what you presented today and the so-called near horizon geometry?
Okay, now I understand. Okay, so basically in this paper that I mentioned by Madison and collaborators, the question they ask is that, okay, in ADS CFT we have many black hole examples, and universally in these black holes you usually have some ADS2 factor, okay, and then this ADS2 factor of the near horizon geometry has some symmetry algebra of killing vectors. So the question was, how do you see this symmetry algebra from the perspective of a dual CFT? Okay, and their claim was that because and of course in some sense maybe motivated by these recent developments with quantum information in ADS CFT, they wanted to ask, are these symmetries somehow related to properties of, I don't know, like entanglement or complexity in states of CFTs? And their proposal and the claim was that actually, if you want to look at the growth of operators in a holographic CFT, the way they grow as time evolution. Okay, so these operators, when you look at these operators, their holographic dual picture is basically some particle or some scalar field moving in the bulk of the black hole geometry. Okay, and basically this, so probing this near horizon geometry is basically could be encoded in the properties of the way these operators in the CFT grow. And their claim was that the examples that they actually analyzed in this two-dimensional holography of SYK and ADS2 was that the momentum of the particle, or well, depends on the coordinates, or boosts of the particle that moves in this ADS2 near horizon geometry is related to this notion of complexity defined by, in SYK, there's a natural notion that is basically like this Krylov complexity, but in a slightly different language related to this boost or momentum of the particle moving in this ADS2 geometry. So they propose that, if we have some good notion of complexity in holographic model, this complexity should be related to the symmetry algebra in some sense, or some generators of this near horizon geometry. In particular, the relation in their paper is between boost or the momentum of this in the near horizon geometry and the growth of this operator in the SYK. So it's some story, but I don't know if it. I mean, it's just some intuition that comes from this lower dimensional SYK holograph.
Thank you.
So perhaps it's time to close this session, at least if there is no other questions. So thank you again for the interesting talk. Maybe relativity was not very strong in this, but at least this ADS appeared, and discussion was also about the correspondence with ADS. Yeah. So thank you very much.
Thanks a lot.
So see you next week.
Yes. Bye.
So thank you.